Okay, so here I have some function f of x, and what I want to do here is I want to find the area under the curve from this function f of x. So how would this be written in calculus? So in calculus, to find the area under this curve, so this area right here, in calculus it would be written as follows, right? I would write this area using this notation here. However, before we can jump to this notation, let's try to find the area under the curve using stuff that we already know. That is limits. We can use limits to find the area under the curve before we can jump to this notation. And we need to jump to this notation because using limits is going to take, as you can see, a lot of time, and it's not the most efficient way to find the area. So in order to find the area under this curve, what I'm going to do is I'm going to split this area into a bunch of rectangles. I'm going to draw a bunch of rectangles, and hopefully this is going to let me approximate the area under the curve. And again, keyword being approximate. This is not going to be the exact area, but it's going to be a pretty good approximation of the area. Okay, so this is just my best attempt at drawing a bunch of rectangles on to cover the area under the curve. And so by doing this, I can approximate the area under the curve. And let's just say that each rectangle has a width that is about equal to the other rectangles around it. So although it might look like these rectangles are smaller, let's just say that they have the same width as the other rectangles. So what I can do is I can take the area of each of these rectangles and I can sum them all together. And I can approximate, by doing that, I can approximate the area under the curve. But as we can imagine in our heads, as if this is n rectangles, as n approaches infinity, we're going to get a better and better approximation of the area under the curve. And as n approaches infinity, we're going to get the exact approximation. And when we see this notation like n approaches infinity, we think about limits. At least I think about limits because we write limits as limit as x approaches a number, or like limit as d approaches a number, as n approaches. This is not a number, but n approaches infinity. We also do that with limits, right? So as the number of rectangles approaches infinity, we're going to get a better and better approximation of the area under this curve. So let me write something out here, and then I'm going to explain what it means. So limit as n approaches infinity of the summation. So why I'm doing the summation here is I'm summing the areas of the rectangles. So I'm going to start I equals 1 to n. This is not going to make sense at first, but I will explain what this means after I write this. Okay, so what I'm doing here essentially is I'm taking the sum of every single rectangle under this curve. So if we have n rectangles, and I'm starting at I equals 1, going up until n, so I represents is indexing each rectangle. So the first rectangle would have an index of I equals 1, and so on and so forth. And what I'm doing here is this represents the x value. So a plus b minus a over n. What is this b minus a over n? B minus a over n. So if we look at b minus a, that's this distance right here. And if we divide that by n, the number of rectangles, what we get is we get the width of each of the rectangles. So that's the width of each of the rectangles. A plus b minus a over n. A is what we start off with. That's the left bound, right? So if we add b minus a over n, so times I represents the index. So if we're talking about the first rectangle, that would be b minus a over n times 1. That would be a plus b minus a over n, basically. And if b minus a over n is the width of each rectangle, that would represent a plus this width, so that would be here. That's the x value that we would consider. And so this is the x value, f of x value. So f of x represents, this whole thing represents basically the length, and then b minus a over n represents, as we said, the width. So this is the length, this is the width. And so if we have a plus b minus a over n, and we are talking about the second rectangle, we would be times 2. And so we get a plus b minus a over n times 2. So that would be 1, 2, we would be here. And obviously this is for the right side. If we were talking about the right Riemann sum, if we're talking about the length when we consider the right side of the rectangles. And so this actually doesn't matter when n approaches infinity. We're taking the limit as n approaches infinity. Now, if we didn't have this portion right here, if this wasn't there, and we just had this summation right there, then it would matter, because sometimes it's better to consider the left side and the right side. When we consider the left side, sometimes we would have a over approximation, and sometimes it would have an under approximation. So we need to consider which side we're choosing. But as the limit, as n approaches infinity, as the number of rectangles approaches infinity, it doesn't matter anymore if we're looking at the right or the left. So this is good. So this is actually going to give us, as n approaches infinity, as the number of rectangles approaches infinity, it's going to give us the exact area under the curve of the function. So this is the important formula that you need to know. And you don't need to memorize this formula once you can understand this conceptually. And I always like to understand this conceptually by drawing this graph out, drawing some sort of a function. It doesn't really need to be a neat function, just some random function, and then just thinking it out. If we're looking at what does I represent, what does n represent, what happens as n approaches infinity, what's the width of each rectangle, what's the length of each rectangle, what's the area, that's the length times the width. How do we take the summation of the length times the width, or the area of each of the rectangles, and how does that represent the area of the under the function over the x-axis.